In the United States, millions of cars reach the end of their life every year. Some are the unlucky victims of highway accidents, twisted and mangled beyond recognition. Others simply grow old, engines worn, frames rusting, electronics failing, until repairs become more expensive than the vehicle is worth. But not all disappear into the shadows. In the heart of America's industrial landscape, there are places where endings are turned into beginnings. Today, we're taking you inside one of the most extreme processes in the automotive world. How old cars are stripped, crushed, and reborn as pure scrap metal. Before we dive in, make sure to hit that subscribe button and turn on the notification bell so you don't miss any of our upcoming videos on incredible industrial processes from around the globe. Trust me, today's journey from a beat-up car to a gleaming pile of scrap metal will blow your mind. Before the real destruction begins, the car is picked apart with surgical precision. Workers move quickly, armed with wrenches, power tools, and an intimate knowledge of automotive anatomy. Every piece that can be reused, resold, or repurposed is removed. The headlights are unbolted and set aside, destined for resale to a body shop. Side mirrors, door handles, and the steering wheel are removed. Small parts that can still command a decent price in the used parts market. Wheels and tires are pulled off, their rubber still worth something to a driver somewhere. The catalytic converter is always a priority. Containing small amounts of precious metals like platinum, palladium, and rhodium, it's one of the most valuable components in a modern car. Mechanics handle it with care, knowing it might be worth more than all the other parts combined. Seats, seat belts, dashboards, all come out if they're in good condition. Even the battery is lifted out and sent to a separate recycling line, where its lead and acid will be processed under strict safety protocols. To a casual observer, this dismantling might seem like unnecessary effort before the crushing begins. But for the scrapyard, it's a vital part of the business. Selling these components helps offset the costs of operation and ensures that usable resources are not destroyed prematurely. Once stripped of its valuable parts, the car is drained of the liquids that once kept it alive. The process is methodical. A suction pump draws out the engine oil, thick and blackened from years of use. Coolant is siphoned from the radiator, its once bright green now faded to a dull, murky hue. Transmission fluid, brake fluid, and power steering fluid all flow into separate containers. Gasoline still left in the tank is carefully pumped out and stored for reuse. Even a nearly empty tank can yield a gallon or two, enough to be worth saving. This step is more than a matter of thrift. Left inside the car, these liquids would leak out during crushing or shredding, contaminating the soil and water supply. Oil can cling to soil particles for decades, and even a small amount of coolant can be deadly to wildlife. By draining every drop, scrapyards not only meet environmental regulations, but also fulfill an unspoken responsibility to protect the land around them. Now the car stands empty, hollowed out, and dry. This is when the true spectacle begins. The crusher, a machine as tall as a two-story house and weighing tens of thousands of pounds, looms over the stripped carcass. It's a simple design in principle, a massive hydraulic press with the power to flatten steel like paper. But the effect is mesmerizing. As the operator lowers the crusher's jaws, the car resists for a moment, then yields with a loud metallic groan. Glass shatters, steel bends, and panels crumple inward. In less than a minute, the vehicle is reduced to a compact rectangular block. This crushing serves two purposes. First, it makes the car easier to transport and store, taking up far less space in the yard. Second, it prepares the metal for the next phase, the shredder. The crusher is not about destruction for destruction's sake. It's about efficiency. If the crusher is brute force, the shredder is precision violence. The crushed car, now weighing over a ton but small enough to fit on a conveyor belt, is fed into a machine lined with rows of rotating, steel-toothed drums. The moment it enters, the noise is deafening, a metallic roar mixed with the sound of tearing and grinding. In seconds, the car is reduced to pieces no larger than a man's fist. Bits of steel, shards of aluminum, fragments of plastic, all mixed together in a chaotic stream of debris. The shredder doesn't discriminate. Everything goes in, and everything comes out in fragments. But this chaos is short-lived. Within moments, the separation process begins. The first stage of sorting is magnetic. A powerful electromagnet hovers over the conveyor, lifting every piece of ferrous metal, steel and iron, from the pile. These are the most common metals in a car, making up the bulk of its weight. Next, eddy current separators push non-ferrous metals like aluminum and copper onto separate paths. The process uses magnetic fields to repel these metals, flinging them into their own collection bins. Finally, what remains, mostly plastics, rubber, and glass, is sent away for disposal or specialized recycling. By the end, every type of material has been separated and stored, ready for the final stage. The steel, aluminum, and copper are loaded onto trucks and sent to smelting plants. There, in furnaces hotter than lava, the metals are melted down. Impurities are skimmed away, leaving pure, molten material ready to be reshaped. Steel might be cast into ingots, then rolled into beams for construction. Aluminum could be molded into sheets for airplanes or beverage cans. Copper might find its way into electrical wiring, powering homes and businesses. This is the true magic of the process, transformation. What once was a car's frame might soon hold up a skyscraper. The metal that carried a family across the country might one day carry electricity to a hospital. Nothing is lost, everything changes. If you enjoyed this deep dive into the extreme car-to-scrap metal process, smash that like button, drop a comment telling us your favorite part, and subscribe to the channel for more behind-the-scenes looks at the world's most incredible industrial processes. Don't forget to ring the bell so you're the first to see our next big transformation story. Until next time, keep exploring, keep learning, and keep seeing the beauty in the unexpected. Glass bottles. They're everywhere, holding everything from water and wine to perfumes and hot sauces. But have you ever wondered how they're made? It all begins with something incredibly simple: sand. Through a complex, high-heat transformation, that sand turns into strong, clear glass. And behind every bottle is a fascinating process that combines precision engineering, intense heat, and a touch of artistry. In this documentary, we're taking you deep inside the world of glass bottle manufacturing. From raw materials to high-speed molding, and from quality checks to packaging, it's a journey of heat, pressure, and craftsmanship. You'll see how ancient traditions meet modern technology in factories that produce millions of bottles every day. But before we dive into the fiery heart of the factory, don't forget to subscribe to Top Discovery 4K for more incredible behind-the-scenes journeys just like this one. Hit that subscribe button, turn on notifications, and let's get started. The story of a glass bottle starts in the earth, with a blend of raw, naturally occurring materials. At first glance, it might seem improbable that such a smooth and elegant product could begin as something as coarse as sand. But that's exactly where it begins. The main ingredient is silica sand, also known as silicon dioxide. This finely ground mineral makes up around 70 to 75% of the glass mixture. The purer the silica, the clearer the resulting glass. But sand alone doesn't melt easily. Its melting point is a scorching 1700 degrees Celsius. That's where additional materials come into play. To make the process more efficient and manageable, manufacturers blend in soda ash, sodium carbonate, which lowers the melting point to more practical levels, limestone, calcium carbonate, which increases the chemical durability of the finished glass, alumina, added in smaller amounts to enhance strength and resistance to wear. But perhaps the most important addition in modern glassmaking is cullet, which is simply crushed, recycled glass. Cullet is a game changer. It melts at a lower temperature than raw sand, saves energy, and reduces CO2 emissions. Some factories use up to 80% cullet in a batch, especially in green or amber bottle production. Colorants can also be introduced at this stage, depending on the final product. For instance, iron oxide gives glass a greenish or brown hue, common for beer bottles. Chromium oxide deepens the green tone. Cobalt oxide is used for blue glass, often found in decorative bottles. These ingredients are blended with precision in enormous batch mixers. Accuracy is critical. Even small variations can affect the quality, clarity, or stability of the glass. Once mixed, the raw batch resembles a fine, sandy powder. It's now ready to face the heat of the furnace, a transformation that turns humble minerals into glowing, molten glass. The real alchemy of glassmaking happens inside the furnace, a cavernous structure that resembles a glowing volcano. These furnaces operate 24/7, reaching temperatures of over 1,500 degrees, 2,732, and consuming raw materials in massive volumes, often hundreds of tons per day. The batch mixture is continuously fed into the furnace using automated conveyor belts. Inside, it melts slowly over several hours, transforming from a grainy solid into a smooth, homogeneous liquid. Here's what happens inside. At around 1,100 degrees Celsius, the sand begins to soften and fuse. As the temperature rises, individual grains dissolve and bubbles form and rise. Around 1 through 300 degrees, the mixture becomes fully molten and impurities are gradually released. By 1,500 degrees Celsius, the batch has become a glowing orange liquid glass, flowing like lava. To ensure quality, a step called fining is critical. This removes gas bubbles and unmelted particles. Fining agents like sodium sulfate or antimony oxide may be used, or the molten glass may simply be held at high heat to allow bubbles to escape naturally. After the glass is fully melted and fined, it flows into a refiner zone, a slightly cooler area that reduces the temperature to about 1,050 degrees Celsius. This creates the ideal viscosity for forming, thick enough to shape, but fluid enough to fill molds without defects. The molten glass is now ready for precision cutting. It's delivered to a feeder, which dispenses the glass into glowing, consistently sized gobs, each one perfectly measured for a single bottle. These gobs, droplets of fiery molten glass, are where form begins to meet function. They drop rhythmically into high-speed forming machines. In just seconds, they will become the bottles we use every day. Now comes the most dynamic and visually stunning part of the process: forming and molding. This is where molten glass transforms into the final shape of a bottle in mere seconds, thanks to precise mechanical choreography. The process takes place on a machine called an IS machine, short for individual section. Each section of the machine operates independently, with its own molds and timing, allowing multiple bottles to be made simultaneously and continuously. Step 1. Gob delivery. Glowing orange gobs of molten glass, each weighing just the right amount for a bottle, are cut from the stream and dropped into blank molds. These molds are made from cast iron or nickel alloys, capable of withstanding extreme heat and repeated use. Step 2. Parison formation. The gob is pushed downward using compressed air or a plunger, creating a preliminary shape called a parison, a partially formed bottle with a hollow center. This step is critical. The parison determines the eventual wall thickness and bottle strength. Two main techniques are used here: blow and blow. Air is used both to form the parison and to expand it into its final shape, common for narrow-neck bottles like beer or soda. Press and blow. A plunger forms the parison before air expands it. This offers more precision and is typically used for wide-mouth jars. Step 3. Final blow molding. The parison is then transferred to a final mold, which gives the bottle its full shape: neck, body, and base. A blast of compressed air inflates the parison until it perfectly conforms to the mold cavity. The bottle's defining features, branding, ridges, threads for caps, are all imprinted at this stage. This entire sequence takes less than 10 seconds and it happens over and over, with remarkable precision. Some factories operate 20-section IS machines producing over 600 bottles per minute. Step 4. Preliminary cooling. Once the bottle is fully formed, it's cooled with a blast of air to solidify its shape. But at this point, the glass is still hot, too hot to touch, and highly stressed internally. If cooled too quickly, it would crack or explode. Instead, the bottles are gently carried out of the molding section by conveyor belts, glowing red-orange and heading straight for a long, narrow oven. This leads to the next critical phase, annealing. Freshly molded bottles may look finished, but they're far from ready. Right after forming, the glass contains internal stresses caused by uneven cooling. Left untreated, these stresses can cause bottles to break spontaneously, even days later. To solve this, the bottles enter a process called annealing, which carefully relieves stress and stabilizes the glass structure. They pass through a long tunnel oven called a lair. Inside, temperature zones are controlled with extreme precision. Bottles enter at around 550 to 600 degrees Celsius, still glowing. Over the course of 20 to 60 minutes, the temperature drops slowly. Air jets and fans control cooling rates to prevent thermal shock. This process ensures the glass contracts evenly across all dimensions: neck, walls, and base. The result is a product that's not only strong, but also durable under pressure and thermal shifts. At the end of the layer, the bottles have cooled to room temperature. They're no longer glowing, and they can finally be touched safely. Now, they're ready for inspection, but not all bottles will make the cut. Every glass bottle must meet exacting standards for strength, consistency, and safety, especially if it's going to hold beverages under pressure, like beer or soda. Even minor imperfections can lead to leaks, breakage, or contamination. That's why quality control is embedded throughout the production line. As bottles exit the annealing layer, they pass through a high-speed inspection system. Here they face a barrage of tests, both automated and manual. Visual inspection cameras and sensors scan each bottle at incredible speed, checking for cracks or fractures, air bubbles trapped in the walls, inclusions, foreign particles embedded in the glass, irregular shapes or dimensions. Defective bottles are instantly rejected and sent for recycling. Specialized machines measure every part of the bottle: neck diameter, thread alignment, wall thickness, bottle height, and symmetry. For certain uses, like pharmaceuticals or pressurized beverages, tolerances are razor thin. Select batches undergo pressure testing, where water is pumped in until the bottle bursts, ensuring it meets minimum burst resistance. Others are subjected to thermal shock tests, where bottles are rapidly heated and cooled to mimic real-world conditions. Human inspectors also play a role, spot checking samples and verifying calibration. Some modern facilities use AI-based systems that learn from defect patterns. These smart systems adjust settings on the fly, improving quality without halting production. Only bottles that pass every test are cleared for packaging. The rest, up to 2–3%, are crushed and reintroduced as cullet for the next batch. Once bottles pass inspection, they move on to packaging. Depending on the factory setup, there are two main options. Some bottles are transferred directly to filling lines, especially in integrated beverage plants, where they are immediately filled, capped, and labeled. Others are packed in bulk for delivery to external clients. Robotic arms stack bottles onto pallets, adding cardboard dividers to prevent damage. These pallets are then shrink-wrapped and labeled with barcodes for traceability. Whether headed to a craft brewery, a cosmetics brand, or a pharmaceutical facility, each bottle is secured for safe transport. From here, the glass bottles begin their journey across cities, countries, and continents, ready to be filled with everything from mineral water to luxury perfume. Glass bottles are not only functional, they're among the most sustainable packaging options available. Made from natural materials, they're 100% recyclable without loss of quality. In fact, a glass bottle can be melted down and reborn endlessly. Modern glass plants maximize the use of cullet, recycled glass, to reduce raw material use and cut energy consumption. Many employ closed-loop recycling, where defective or returned bottles are crushed and reintroduced into the batch. Some manufacturers also develop lightweight bottles, using less glass while maintaining strength. Recycling rates vary globally, from over 90% in countries like Sweden and Germany to around 33% in the US, but every recycled bottle makes a difference. From grains of sand to shelves in stores, the glass bottle's journey is a remarkable blend of nature, engineering, and sustainability. Each one is born from fire, shaped by precision, and designed to be used and reused without compromise. So next time you pick up a glass bottle, remember, you're holding more than a container. You're holding a story of innovation, responsibility, and endless potential.